Okay.
Welcome at this second meeting of seminars around COVID and data and modeling. My name is Marc Salomon. I'm representing Amsterdam Data Science. A little bit about Amsterdam Data Science. Amsterdam Data Science is a cooperation between the University of Amsterdam, the Free University, the Hogeschool van Amsterdam, and the CWI. We together work across all areas of data science together, both in research and in teaching. And before I forget and give the word to Lucas from Amsterdam Medical Data Science, I wanted to mention and I want to thank our sponsors, that is Google, Elsevier, Amsterdam Data Science, of course, and Amsterdam Medical Data Science for making this seminar series possible. And here on the screen, you will see the program of today. And I will now give the screen to Lucas to introduce Amsterdam Medical Data Science and also say a few words about COVID.
Thank you. So my name is Lucas. I'm a medical resident in the intensive care unit and part of Amsterdam Medical Data Science. And Amsterdam Medical Data Science is in its board are Marc Hogendoorn and Paul Elbers from the VU and the Amsterdam UMC hospital. And I think it's a great opportunity that we can co-host this meeting together with Amsterdam Data Science. And I just wanted to give you a very brief introduction for today, but I want to leave most of the talking to the speakers of today. And I think the topic of today will be COVID. And as many of you know, it's hit us hard over the last few months, especially in the intensive care unit. We had a lot of COVID-19 patients. So I think it's great that these initiatives are there to see if we can use data to actually help these corona patients. And for this, we started a large initiative where we cooperate with hospitals in the Netherlands. And it's really a project by all hospitals in the Netherlands. And currently you see some logos from all the hospitals that are currently participating in sharing the data regarding corona patients to see if we can use data science to actually help these patients to better predict their course during their hospital stay and see if we can optimize their treatment. And as of now, we have about 1,500 patients in the data set. And Daan will talk a little more about processing of the data during his talk. So we're really excited to be together with Amsterdam Data Science and all of you guys here today.
So yeah, Daan is Daan de Bruin from PacMed. We'll talk about his experiences with the application of machine learning in the context of COVID. And Daan, please take the screen.
Thank you, Marc. Hi, everyone. I'm Daan. I am lead data scientist at PacMed. And I hope you'll see my screen. And today I will talk about our project together with Amsterdam UMC to build a Dutch COVID-19 ICU database and all the challenges we face doing this, solutions we built, and opportunities coming from this database. So first, a little bit about the ICU. I think everyone knows in the ICU, patients that are in critical conditions are treated. And the nice thing for us data scientists is that the ICU is a very data-rich environment. So here you see an overview of some of the things that are measured in the ICU. You have a patient, just normal patient characteristics, but also vital signs and device data. Data coming from the machines the patients are on, like the respiration machines or the blood pressure measurements, the heart rate measurements. Medication is registered in the ICU. Lab values, so lab tests, blood tests are done multiple times a day sometimes to really assess how the patient is doing. And the nurses and doctors have their clinical observations, and which they also register about how the patient is doing. So for data scientists, it's a very nice place to be because also patient measurements are recorded in very high frequency and high quality. For example, data from the machines are saved multiple times a minute sometimes. but also lab tests are registered very well because it's such a critical condition. It's essential that the data registry as well. So the data is very high quality. And as PacMed, we therefore do a lot of work in the ICU. We built prediction models, machine learning models to help doctors treat patients in the ICU, and then build software products to help doctors make decisions based on machine learning. And we were doing that before COVID for a while, but then COVID-19 entered the stage. And for us as PacMed, this changed a lot because, of course, our normal ICU work was not so relevant at this moment. And COVID-19 is also a very special situation for the ICU because actually a lack of experience. So there's little known about effective treatment of COVID because it's a new disease. Individual doctors also have only little experience. Also still now, maximally maybe doctors have treated 50 patients or 100 patients, and they just on their own, they don't have a lot of experience. Also for individual hospitals, there's only little data to learn from. Again, 50 patients, 100 patients maximally, and little time for doctors to do research. And this is really different from the situation before, where we could, with this data of a single hospital, had access to historic data of tens of thousands of patients we could learn from. And now a totally new disease, it's different. And to get meaningful insights, we think ICUs have to work together. And therefore, the Amsterdam UMC initiated a consortium to work together in this, together with all or most of the Dutch ICU, gather knowledge about effective COVID treatment. So we formed a consortium, Amsterdam UMC, Maastricht UMC, but also the Dutch ICU organizations, NVIC and NICE, a lot of the Dutch ICUs, and some machine learning partners, the VU and the University of Cambridge, all working on with the same goal: can work together with all Dutch ICUs to gain knowledge about effective treatment of COVID-19 in the ICU. I will tell what we did and what we achieved. So this is the hypothesized infrastructure. So we get on the left 75 ICUs in the Netherlands, which use 3 different electronic health record systems, which all flow nicely together into one centralized database with thousands of patients, which is then made available to doctors, researchers, data scientists, really open source almost, to do research on to improve treatment of COVID. What was important here, so this all looks relatively easy, is that it didn't cost time for the intensivists or for the people in the ICU. So what we did, we tried to achieve that by building, first of all, queries that they could launch on their source system. So really on their Metavision, Higgs, or Epic system, we gave them an SQL script which they could run, export, and send it to us to be used. So this is an example of this of such a script we made for them, and this actually went pretty well. Already more than or almost 30 ICUs have delivered their data, and here you see them, and almost 30 more are in the process of delivering this. So I think this is already a very nice achievement that, yeah, really the Dutch ICUs are working together in this scale for the first time to fight COVID. This resulted, as Lucas also showed, in data of over 1,500 patients. So yeah, it started to be big enough to do meaningful insights, make meaningful models. And yeah, so this all looked maybe relatively easy, but what we really experience is that with so many data sets of so many hospitals, everything that can go wrong will go wrong. So I will also talk a bit about the challenges we faced. For example, corrupt exports. Something just went wrong while exporting the data, or a table was missing, a column was missing, headers were forgot to export. Data was too big to export, so they were sending maybe multiple files. A small mistake was made in the patient selection. All of these problems happened in like a couple of hospitals, but if you add this all up, these were big headaches for our data engineers who had to cope with incoming data sets every week of 30 hospitals. So this was a very big challenge for us, which is all solvable, but just made it a very big challenge. And the second challenge was the data of different source systems just differs a lot. Here you see the 3 source systems, which tables we got from a hospital. First of all, you see that for Epic and Medivision, it's a lot of tables, and they are all different from each other. So what we built is a ETL pipeline, which transforms the raw hospital data into a structured combined database. So here you see on the left the raw data coming in. Every week, a hospital sends an update of their data, and it's either a Higgs, Epic, or Medivision set of tables. And we process that into a structured format, into 6 different tables with all the same column names, all the hospitals nicely under each other in one database. Big challenge here was being able to cope with the workload. Datasets are really big, tens of millions of rows per hospital, sometimes hundreds of tables per hospital, and every week an update coming in. So in order to distribute and be able to handle this workload, we used tools like Airflow, which is an orchestrator you can use to manage your scripts that are running, and Docker Swarm to distribute the work over multiple machines, servers. And then we have this nice combined database. Are we done now? Well, the answer is no, because also the content of the data was very heterogeneous. As an example, here you see the different ways the parameter pH, so blood gas, is found in the different hospital datasets. And here you see that every hospital uses their own name for the parameter pH, or sometimes hospitals use multiple names actually. And there's no uniform parameter ID or mapping available to be able to cluster this to say, okay, this is all about pH. So, and this is only one parameter, but we wanted to use hundreds of parameters. So this turned into a huge mapping process, which we had to deal with. So we made big Google Sheets where we had on the left the parameter name in the hospital, and then on the right the parameter it should be mapped to. And this, we first tried to automate this just by looking for text strings in the parameter. However, it turned out that that was not good enough. Too many mistakes were made in automated mapping. So this whole process happens partly manually, where ICU doctors also from the VU just go through all the parameters, map them to the right category, so that we can use them in the database. It's not only that. Apart from parameter names, also units need to be converted. So some hospitals measure weight in kilograms, other measure it in ounces, or for example here, Untitled CO2. Here you see the distributions of the values for different hospitals, and you see on the left some hospitals that measured in I think it's kilopascal. And on the right, you see some hospitals measured in a millimeter mercury. And so we made all of these plots to find out, did we standardize the data well enough? Because not always units are registered well in the hospital dataset. And again, for hundreds of parameters for 30 hospitals, this ended up in a very big task, where a lot of doctors are also involved. And then last but not least, not only parameter names, but also parameter values need to be mapped. So here you see different values for the parameter ventilation mode, so the setting of the ventilation machine. And one hospital already uses dozens of different settings, but they actually can be placed in 2, 3, or 4 categories. So the mapping of this ventilation modes to categories was again a manual step that has to be taken on for all the hospitals. Well, after this huge amount of work, we have now created a data warehouse, which is a cleaned and standardized data set in 6 different tables. And this database is made available to researchers in a data warehouse to be able to facilitate research to better treat COVID patients. And this data set is really rich. So we just started with analyzing, with modeling, but we already see that the data is really rich enough to draw meaningful conclusions. Here you see, for example, analysis you can do with this data set. So you see the average oxygen fraction administered to patient during the first 2 weeks of intubation. And in the blue line, the patient that survive, and the orange line, the patients that do not survive. And you see after 1 week or so, they start to deviate. So we can distinguish these patients already quite well long before. And not only these kind of insights, we also see that there's a huge difference in how patients are treated in the ICU. For example, if you look at specific medications, some hospitals always use medication for a certain patient, for all the patients, whereas other hospitals never use this medication. And there's also a big difference in how patients are treated, with how the ventilator is used. So this shows that there's a lot of potential to learn from the differences in how hospitals are treating the patients. So that's what we're currently doing, building with a lot of external researchers, build various machine learning models. Here are a couple of the research questions we work on. Which patients benefit from being ventilated in prone position, so on their belly, or lying on their belly instead of lying on their back? Which patients are at risk of getting a lung embolism? When can I extubate a patient safely and when not yet? What is the remaining time the patient will stay in the ICU? And very importantly, which medications or which treatment strategies work for which patient groups? And what is survival probability of this patient? So all kinds of problems we can now hopefully answer or partly answer with this data set. And the team, in order to do this, grew and grew the past weeks, because the challenge turned out to be much bigger than expected, especially this whole mapping process. So we have a lot of doctors involved internally in PacMed, but also externally at the UMC. A lot of data scientists, a lot of data engineers, also external research groups, the VU led by Marc and the Cambridge led by Michele van der Schaar, to really get the most out of the data, also in terms of estimating causal treatment effects. As I said, this turned out to be a much bigger challenge than expected, and also we had hoped to have already earlier results, but because of all the challenges mentioned, this took a bit longer. And in the meantime, also the amount of COVID patients in the ICU did steadily decline, luckily. So the question is a little bit, how is this? And this is my last slide. How can we still be relevant with this research? Well, I think there's various there's a couple of areas. First of all, we will be better prepared for a second wave. Let's hope it does not come, but if it comes, I'm certain with this research we will gain a lot of knowledge which can be used to better treat COVID patients in the ICU. If that not happens, we can improve the treatment of a steady small amount of COVID-19 patients, which will stay probably for a long time in the ICUs. Third is internationally, we will publish our findings in academic papers and to help other countries also better treat COVID-19, where it's still a very big problem. And last but not least, we think by doing this project, we facilitate future large-scale ICU machinery research in the Netherlands. Because now hospitals are working together, we have this infrastructure built. We can do much larger scale machine learning research to improve general ICU treatment and to be better prepared for future pandemics. This was it, and I'm happy to take questions, but I think I am already out of time, so this is safe to.
Very nice. There are many questions. Probably, I don't know, Julia and Jane, whether you have ordered them a little bit and could ask to Daan some questions.
Yes, so we have some that have been upvoted, so please do upvote any questions you see that you particularly want to know the answer to as well. So we have one from Anna Grotenhuis. Do participating hospitals have access to the data to do analysis?
Yeah, good question. And yes, they have. They have to sign some legal documents, etc. And but they do. So the whole idea is that the hospitals are that we do this with the hospitals and for the hospitals, so that no one owns the data or has IP on it. That it's for the general use. And not all hospitals are accessing the data, because you have to have some research team to do so, of course. But a lot of them already are. Yeah. Yeah. Good question.
And a particularly popular question is, how did you deal with the confidentiality in patient data and GDPR regulations?
Yeah, very good question. I forgot to mention that. Yeah, so we only receive data for which the identifiable information is removed, but still we had to, this is very sensitive data. Data is stored on servers with the highest security. And there has been a exception made by the Dutch Authority of Personal Data, that because of this crisis, because this crisis is so big that this is allowed. Normally, this is prohibited, but because of the crisis, it's allowed this time.
And another is, what is the time, effort, skill required for each stage of this project? From problem, concept, hypothesis generation, data collection, structuring, model building, and hypothesis verification and reporting results.
Yeah. Yeah, so yeah, really different skills are needed. So for the data engineering, for the combining of the databases, you really need experienced data engineers who know how to deal with Airflow, with databases, with Docker, etc. And but in the step after that, there's really a big role for medical specialists. So this mapping process. Yeah, we have about I don't know, maybe 10 different medical experts from medical students to ICU doctors working on this, because of the mapping step. And after that, it's more of a machine learning project where you need a good data scientists and professors that know how to deal with observational data in healthcare and how to all the limitations and to get the most out of it. So it's really a mixed skill team.
And I think one last question before we go on to Bjorn's talk. Given that it's pandemic, why do we collect data only within Dutch borders? Does it only have to do with differing data protection regulations, or are there different approaches to treatment also an issue?
Yeah. Good question. Well, I think in the EU, it is possible, I think, to in the same way share data with each other if you get the proper legal documents. But practically, it's of course very hard to organize to get everyone on board. So therefore, we said now, okay, let's only do it with the Dutch ICUs, and when we have that in place, maybe look abroad, see who wants to join. And different approach to treatment, yeah, probably that's also an issue. I'm not sure. I think already in Netherlands there are really different ways patients are treated, but maybe the difference is how ICUs are organized is also
maybe it's good to mention that all hospitals within the EU fall under the GDPR. So in that respect, if they're under the GDPR, we could also gather data from hospitals outside of the Netherlands within the European Union. and that all data is pseudonymized. So we do not get name or address or any other sensitive data from these patients. So they're pseudonymized in the hospitals that provide the data, and that there's an opt-out procedure so that all patients through media and through posters in the hospitals are aware that this research is going on, so they can always opt out and they can decide that they don't want their data used. So our next speaker is Bjorn van der Ster. He is from the Department of Anesthesiology in the Amsterdam UMC, and he will be delivering the next talk for you guys on predictive modeling for COVID-19 patients. So Bjorn, the stage is all yours.
Thank you. Thank you for the invite as well. They just started some heavy construction next door, so I hope that doesn't interfere with the clarity of my voice. So yes, I hope you can all see my screen. As I said, I work with the Department of Anesthesia at the Amsterdam UMC. For some of you that expected my direct colleague Bart Geerts here, he unfortunately couldn't make it, so he asked me to do the talk today. And we're working on our Under the Weather project, which he may have discussed and showed to you in an earlier stage, and how that led to the Windfall project, which some of you may have heard of. So earlier we were working on this Under the Weather project, and basically the fundamental question that we had with it was, can weather predict emergency department crowd? And the reason behind this, because we had some anecdotal evidence that, like for example, at the departments of cardiology, they said we see more patients with heart failure, decompensation, of course, after or during the herring season, or we see more an increase of motorcyclists breaking all kinds of, having all kinds of fractures after the first summer days. So we sort of figured there's a time and weather correlation or association that we can use to predict when patients will present themselves to emergency departments. And another example, the temperature variations in higher humidity have shown in previous literature and previous research that it increases the stroke hospitalization rates. So what we did is we worked together with the Netherlands Institute of Statistics, the CBS, and they created this big patient database for us that covers the data of all patients presenting themselves to the emergency department in the Netherlands over the years 2010 to 2018, covering 16 million visits, 570 different types of diseases, DBCs, over 24 specialisms, and this data is publicly available for all of you data scientists and machine learning enthusiasts. And we combined that with the Weather Institute database, the KNMI, the Dutch Meteorological Institute in the same years, and they do a very nice distribution of daily data on 40 different features. So for example, the temperature and humidity, but also rainfall and sunshine. And they have stations set all across the country. So you can, on a very local, regional basis, combine weather correlation with presentation on emergency crowd or COVID presentation. So our next job is to do the feature engineering on these two data sets. For example, check when the public holidays are, the vacation days are, what is the influence of different seasons and different temperatures, but also matching the dates with sporting events, for example. Then checking if the variance and trends of weather over the past few days or weeks predict how many patients of a certain disease will present themselves to the ER. And for example, you can look at acute changes, you can do all kinds of things with these sort of data, of course. And also this data set is publicly available and accessible through an API that can be directly used in Python. And to give you some insight on this, for the incidence of ischemic stroke over the year, so this is the average of 8 years, you can see that in the summertime, I'm not sure if you can see my cursor as well, but in the summertime you can see that there's a decrease, and you can also for each individual holiday, so the May vacations and the February spring or skiing vacation, carnival vacation in some regions shows a decrease. So there's some things that can be learned from this data. more in the line with the COVID prediction. Just before the crisis hit, we had a model that tried to predict the flu pandemics, which are shown here in orange. And you can see about 10 to 12 years of data. And we got from the RIVM the dates that specific flu epidemics hit. And our model trained on weather can, in almost all cases in blue, detect weeks in advance when such an epidemic would hit. Only here it was missed. And here it detected an epidemic that didn't actually happen. So all of that information, we decided to use this same sort of approach to the COVID-19 spread in the Netherlands. And we started this in early March when we just got the data from China, Italy, Iran. And we saw a lot of difference in how countries were treating this disease and how they were applying measures. So we, as we see in this figure here, you can see a lot of difference in speed in which the disease spreads across countries. And you can see how different countries sort of treat everything differently. So we thought, well, we already were working on this influence of weather on other things. We can try it here as well, but also go further and check what are the influence of local measures that each country applied. Do demographics matter? So the population that you have, is it an old population on average or a young population? What is the public health situation in each different region, or is it even something else that we can detect? So after, well, now we can make the same sort of graph for the Netherlands. So if you look at the big towns, more than 200,000 citizens, synchronized to when the first 25 cases arise, we can see there's a lot of difference for the Netherlands cities as well. For example, the Groningen one is a very flattened curve, to sort of say, because it was probably the least hit region because the distance between Brabant was bigger and they had more time to prepare and they weren't hit as or overrun as quickly. But if you look at the smaller towns, you can still see there's a huge variation and spread in all of the different municipalities that we have. And we figured, well, why is this the case? What can we learn from the spread in each municipality? The worst hit parts, the worst hit municipality in the Netherlands corrected for the population size per 100,000 citizens is Heerde. And you can see this in brown, and this even goes quicker than most big towns in the Netherlands, of all of them actually. And it goes off the charts and you have to zoom out to even look at it. And it took longer as well for sort of flatten out. And why is this growth, as we call it, is this spread rate, why is it so big for Heerde compared to other cities? What happened there? So first we checked on what is the influence of weather. This is a result from a ridge regression to sort of select features from the weather database that we had. And the previous day, so which is by far the most significant parameter. The previous day of infection sort of means that yesterday sort of predicts very well how many infections there will be today, which is obvious. For the other parameters you can see here is positive correlations for wind speed and negative for wind direction, which we couldn't really clarify or explain. And we saw negative correlations for the duration of sunshine. I should explain that blue means 1 day in the future, brown 2 days, and green 3 days. And you see the inverse for the percentage of longest sunshine and a negative correlation for the max rainfall. But all of these were sort of circumstantial and not really that strong. So we saw no real clear influence on weather, just on weather compared to other parameters. Then we decided to check the demographics for each municipality as well. And the CBS and Stadline, they have a nice database that gives you all the data, what do you call this? What the population and public health situation is in each municipality. So for example, do you have a lot of diabetes patients? What are the age of your population? Heart patients, lung patients, all kinds of things. There's a lot of information, so let me remove the redundant ones and look at the sort of relative age parameters. We can see that if you have a lot of young people in your population, the spread is slower. The same goes for a lot of, if you have a lot of old people, but sort of in the age of 20 to 45, we saw positive correlations, probably because this is the age group that still has to go to work. They sort of were the ones that couldn't really opt out of all of the implied or the imposed measures. And we see an increase that with increasing population density, so more people on a per square kilometer, we also saw an increase in the spread speed. For the heart patients, that's shown in this section, couldn't really find as clear correlations. The same was for the lung patients. We didn't really see a one universal sort of solution for this. So we added further. We also decided to look at the elections of 2017. So if certain parties, certain ideologies may have contributed to the correlation growth. And you can see that with this, I'm sorry for all the English speakers, and this is sort of in Dutch, so this is the amount of voters in each municipality, and then the fraction of how many voted for each individual party in the Netherlands. And you can see that the more left-leaning parties, not obviously, but clearly stand out with having a negative correlation with growth, and other parties are shown to have a positive increase with growth, which, well, take this with a grain of salt, of course, but we are sort of thinking that maybe there's sort of underlying ideology that can explain why people adhere to applied measures by the government, for example. So what we did is we were interested in why do certain municipalities grow faster than others, and we fitted two regression models, one that estimates the growth factor for each municipality, and one that estimates the final number of infections. And with these two numbers, you can draw a sigmoid line within these two estimated values, which is then sort of fitted or optimized for the spread speed that was found in this municipality. And you can sort of describe from day one on how the spread will be in each municipality, with varying accuracy, of course. For example, Rotterdam, you can see in blue is our fit or our estimated progression of the municipality. And in orange was the observed spread speed and the final result after 90 days, 80 days. And you can see that it sort of underestimated the number of cases that it would expect in a city as big as Rotterdam. Similarly, for Amsterdam, it sort of underestimated, so there were less cases, or overestimated in this case, so there were less cases. But you can see that the overall trend sort of, and the growth rate is pretty well estimated from this. Unfortunately, this model is still very much imperfect for a city in Hoorn, which is more in the north. You can see that it's very largely overestimate the number of cases that you would expect in a city as big and as densely populated as, for example, Hoorn. So this fit doesn't really work here. And so we're thinking, how can we improve on this? By, for example, using the latency and the distance to the initial region. So the initial region is the southern part of the Netherlands, which was initially hit the hardest, and the other parts had sort of more time to see how bad it was and adapt to it. So we want to add this distance or the latency, so the time it took from the cases in the south to move to each individual region, to make this sort of growth estimation more accurate. And of course, we're interested in new interactors of growth, of other factors that could influence this. And of course, take into account the local measures that we don't have in the model right now. Well, all of these graphs can be found on the Windfall website, which is this chart of the Netherlands, updated daily with the number of cases, and going back all the way to March 8. And you can sort of see the spread over time, and check different municipalities on how they did for all of the situations. And you can see the measures that the government sort of imposed in orange here. We do a future prediction of the number of cases for each municipality. So we can see that, for example, Bunnik here has 45 cases now, and it will have 45 cases in one day, 45, so slow, the growth is really slow here. 45 cases for the 3 days in future. Look at Amsterdam, might be a bit more interesting. Let's drag this to the side. We can see that there are 26, 23 infections at the moment, and is expected to grow with about 10 each day. You can select different maps, so hospitalization rates, patients that deceased for each municipality, and check the different types of regression methods that we use. If you indicate the hardest hit region, you can find here really easily. And you can see over time how it changed from being in Brabant, and I hope this is visible, from Boekel around mid-April to where it is now and still is in Heerde. And well, you can animate this entire map and see it over time. Well, I think that's what I wanted to show you. So we're still working on this website and seeing how we can improve this. And we're mostly focusing now on, because the first wave has mostly vanished or it's mostly gone. We want to sort of check which regions are the most prone to having a second wave. Where was the growth the biggest the first time, and are we expecting the same sort of growth for a potential second wave? And this is my last slide. So if there are any questions, I will happily take them now.
Thank you so much, Bjorn. Yes, so we have some questions in the Q&A. So do you also look at acute care admissions of people above 75? If not, would you care to collaborate with the Elsevier project?
We try to make it work all on publicly available data. So we didn't use any sort of departmental or hospital sort of data. Initially, the idea was to build a sort of hospital like ziekenhuisbed checker, so that you could see where the hardest hit regions are for hospitals. But as soon as the wave sort of vanished, the first wave vanished, we sort of pivoted to more looking at why was it that in certain regions the spread was bigger than in others. I'm not familiar with this project, so we can reach out to us, and we'll see if we can collaborate.
And the next question is, where did you get the raw data for the patients per municipality per date? As apparently the RIVM site only reports in a PDF?
No, you can download an RIVM. The RIVM distributes a CSV file every day for infections, hospitalizations, and deceased patients per day per region, per municipality. So we had a little Python script that downloaded it each day, because you couldn't go back on the website from the RIVM. And when we missed one, you can directly mail them and they will send it to you. So, and I think by now they have a sort of different pipeline, so you can go all the way back in time to get all of the data that they published. So yeah, publicly available.
Fantastic. And did your team take into account the possibility of certain particular religious events at the time in the vicinity of Heerde and Northwest area?
The Northwest area. No, we don't have certain like specific events because it's pretty hard to sort of combine all of those for each municipality. But we're working with an organization that is taking into account local measures per municipality. So each municipality can sort of decide on their own whether they close campings or not, or some things aren't like federally or nationally managed. So we're trying to get those data and see if we can add that. But adding specific like single events is pretty tricky. At least I don't really know how to implement that right now. So it will be hard to predict on certain like incidental events.
And did you consider the correlation between various variables? For example, a region is highly related to age, health, and voting behavior.
Yeah, so that's why I used sort of rich regression models, which sort of supposed to correct for multi-collinearity within the features. But yeah, it's a good point that all of these things sort of have a high correlation within each other as well. So we should take that into account, yes.
I don't know if Lucas wants to ask some of his own questions or open up the panel discussion between Daan and Bjorn. No? Okay. There is another question here. You standardize from the first 25 cases, but isn't that very dependent on how much testing is done? Wouldn't it make more sense to standardize according to the number of hospitalizations?
Oh yeah, that's actually an interesting point. Yeah, it's actually a very good point to sort of check that. I hadn't really considered that myself. Yeah, we standardize mostly for visualization in that graph, but it's a good point that testing sort of varies over all of the regions. So and wasn't widely available in the beginning, so there's some bias there on who gets tested and why. Yes.
And how helpful and what would be the limitations of using the regional modeling you have developed for the first wave and apply it to the future potential second wave?
Everyone asks us this. I think the growth rate is a very interesting parameter to look at when you look at a potential second wave. So you can sort of expect, I think the best way of predicting the future is sort of looking at the past. So probably the regions that were hit hard the first time are more prone to get hit hard the second time as well. And we have to sort of, we can sort of look at why here was hit the hardest and prepare them and tell them to do things differently, for example, this time. So that's why I think it's important to learn from this first wave, which was going to happen no matter what. And if the second wave happens, that we can sort of account and manage it better.
Great. And another, have you done an impact study already for using your prediction model results?
An impact on what?
If Pushkar could clarify, that would be great.
We tried reaching out to the government as well for collaboration on this, because we were already working on before they announced their dashboard. So we reached out to them, but we haven't really heard back to them on any collaboration measures. So unfortunately, we don't have any impact yet on policy or stuff like that, if that's what he meant.
Great, thanks.
So I think we've had most of the questions from the people that are in this meeting. So we have a couple of slides that we would like to show. I'm not sure if we can put up those slides. So I think the first few slides we've seen, and I think it's great that we've managed to make this an online session. Our last session was live with Amsterdam Data Science, and now we've gone online in a digital world. So first of all, I'd like to thank Amsterdam Data Science also for helping us setting this up. And I would like to use this opportunity to say that for the Corona project, we've actually been able to get funding to hire more people to be on board in this project. And so first of all, we have a postdoc positioning opening up. It's on the slide. It's postdoc machine learning and health collaborating against Corona using intensive care data. Postdocs with a machine learning background or interest in the medical field are more than welcome to apply for this position. And we also have a second positioning opening up, which is on the next slide, which is a position for a doctor who also wants to do clinical work and work on the Corona project. So this is another project that is opening up. You can find both of the projects on the Amsterdam UMC website, both the vacancies. And I have one more slide. They're also on the meetup page. We posted a LinkedIn link to the vacancy. So if any one of you is interested, please go and check out the vacancies. And I think last thing for me to say is to thank everybody for their attendance today, and also thank the Amsterdam Data Science and the board of Amsterdam Medical Data Science for making this happen. And obviously to our speakers, Bjorn and Daan, for their, I think, really interesting talks on this topic. So I'd like to thank you for your presentations.
And yes, and thank you again to Daan, Bjorn, and AMDS, Google, and Elsevier for helping make this a successful webinar.